So what we'll be learning this semester is we'll be looking at the assembly language, which is using x86 processors. So we'll learn more about this when we come to the coding part, where we have to, yeah, write the coding. So basically on assembly language, we'll be more focused on the difference between high level language and uh, machine level language, right? But this is not exactly a machine language, but then it's closer to the machine language. So we'll be comparing this assembly language mostly with the high level language. We'll also be converting the high level language to the low level language. So in other words, most of the languages that we're going to be using, it's like C++. How do you convert C++ to assembly language? So it means that now we'll need to go back and look at some parts of C++, but we're not going to be looking at everything. We're just going to look at loops. How do you convert if loops, for loops, while loops, and so on? Because in some case, you'll be given a code and they say convert it. If I'm not, maybe it's 20 marks, right? They say convert this C++ code to a assembly language code, or they give you a Java code. They say convert it to assembly language code. So we should be able to know if I have this, how do I write it in assembly language and all that. So as you can see, chapter one is basic concepts. And so let me come down. So on the overview, we just look at some parts which I've mentioned already, which are part of the welcoming language of assembly language. Then we'll be looking at the virtual machine concept. Then we'll look at data representation. So on the data representation, you know those things of binary operations, you know the hexadecimal, octa, and so on, the decimals. So you must know how to convert from binary to decimal, binary to hexadecimal. So we're gonna be looking at those. Also, you can be asked to convert. So those are some of the things which we'll be revising, which you have done in the previous level, right? So also, we look at the Boolean expressions, the Boolean operations. So these also also learn them in SC, or those who are doing scope, I can say scope or SSC between those two. So these we have learned them where we look at the gates, we look at and or not or one and so on. So we'll be looking at those the binary operations where you look at the negations and so on. So yeah, I believe that these are the simplest because we've already also we covered them in SMT012 and also SMTB000. You've covered these truth tables. So now when we come to assembly language, usually I'm not gonna go through, I'm not gonna use this slide right now. I just want to look at a few things here which we're gonna be looking at. So you can see that the first, actually the third page, they present to us to some good questions to ask, like what kind of a question can you be asked, or what kind of questions can you ask yourself, or the type of things which you should be able to do in, or the type of questions which you should be able to answer after this chapter, right? So also you must know how, why am I learning assembly language? What background should you have? As I said, the background to this language is you must understand C++. You must have done SC or scope, right? And also what is an assembler? So usually first semester we learned about compiler. So this time we can be talking about assembler, which is just a language that is going to be converting a high level language to assembly language that we're going to be using in assembly. So now the thing comes and say that we must be able to compare or differentiate between assembler and a compiler. They can ask you what is the difference between an assembler and a compiler, something like that. Then also, what hardware or softwares do I need? These ones will be looking at them when we come to the coding part. What hardwares and softwares will I be needing for these? But for the hardware part, you just need a computer. That's all for now. Just need a computer. And then the softwares, we're gonna be downloading those softwares that we need. Also, you can also use with CMD and so on, command prompt, right? Then you come to what types of programs will I create. Now, these will look at them on what type of programs will I create. Also, this will help us know that if they ask you a question in the test, Remember, this type of questions here with codes, they come with nothing less than 10 marks. So if they ask you, they can ask you a code and say the 20 marks. They do that a lot. Say 20 marks. I mean that if you enter a test room without knowing how to write codes in assembly language, you'll have a problem, right? And also, what do I get with this book, right? And also, what will I learn? So as I said, you'll be learning how to convert the high level language to assembly language. So this, as I said, this language is the one that usually it's more faster than the high level language when it comes to accessing the computer architect. So that's why this is called the module is called computer architecture, right? So this is the closest to the machine language. So now here we'll learn on, as I said, how to relate this assembly language to a machine language, right? And also how do C++ and Java relate to AL. So we must be able to know how do they relate. If you know how they relate, you can be able to convert. And also, is AL portable? We learn that. Why do we learn assembly language? You also know that question. So when it comes to comparing, right, we're gonna be looking at some representative of applications, the applications that you can work with when you're using assembly language or high level language, right? So the first part is the business application. You know that you have applications that are based on businesses, right? That are for businesses and all that. So you learn about those ones. The hard drive, the hardware device driver, and also the business application for multi platforms. So you have the ones for single and multi platforms, and also you have embedded systems and computer games. There are some that can create computer games using such language, right? So you learn about these and also those embedded systems. So now the thing that we should be looking at here. So after this slide, I just wanted to get you the slide and then we can move to the other part. Because on the other part, I on the other slides I tried to uh, summarize this slide as possible as I can. So when we come to comparing assembly language to high level language, right? So what we should look at are the types of applications. So you're gonna be asked. Usually this question comes every year. Every question paper, usually every test one has it. If you can check all the previous year's test ones, it's always there. Even say in class, I will tell you it's there. You must be able to compare this. You want it as it is, right? So the reason why I believe that the reason why he keeps on bringing it back, he knows that even though people knows that it's gonna be there, the majority might not even be able to write it. Is that right? So so what I can tell you now, right now, is that if you start uh, I don't know. You can use many approaches. Some they prefer memorizing first. Some they prefer writing this down multiple times. Some they prefer going to the internet, trying to understand what is happening between the assembly language and the high level language. Then that's when you can be able to compare this. Or some they just read it through and then it stays, right? So it's up to you how you do it. But what I can say now, let's look at what we are provided with here. So the first application that we'll look at, so we look at the business application software, right? This. We look at the business application software. So here they say that the business application software written for single platform. So this is from medium to light science, right? And look at the one that is written for multiple platforms. This one is different operating systems. So let's look at this one first. So when we check for the high level language, right? We check that here we're using the formal structures, right? But then on assembly language, we use minimal formal structure. So when it comes to using the formal structures, we see that this one makes it easy to organize and maintain large sections of code. But then when it comes to using the minimal formal structure, so one must be imposed by programmers who have varying levels of experience. Then this will lead to difficult maintaining existing code. So what they're trying to say is that when you're busy using these minimal structures, right? You should be an experienced coder for you to be able to maintain this code, right? So that's why this will lead to difficult maintaining existing code. So That's why it will be difficult to maintain. So here's the thing. When they say that when you're writing a code, it should be user friendly and all that. That's trying to say that whenever, let's say maybe you pass away, right? And then the the upcoming person who's gonna be looking at your code should be able to understand what were you trying to do, and they should be able to develop the code going forward, right? They should be able to to to, to do this. So they should be able to change the code and all that. So, or to enhance it. So now this makes it uh, more easier to say that when it comes to business software as data written for single platform from medium to large, high level language is the best option to choose. Is right? Because these ones they make it easy to organize and maintain that section of code. So if we check, mostly in high level language, you can write lines that are too long, right? But when you come to assembly language, you realize that most of these lines are not too long. You just realize that this is like, you remember on your exam, right? SCOA021, there was that last part of code generation where you had to talk about move, you move something into something. Let's say you move into register one, you move register two into register one, or you move A into register one. You see, right? So this is assembly language. Now you're gonna be learning that language in detail here. So this language does not contain large sections, or it doesn't contain long codes. So it's gonna be there, being difficult for you to write to manage this code or to maintain it. And also remember with high level language, if you wanna write while loops, you just write while, right? But when you come to assembly language, you're gonna be using codes like L1, and then you loop. It's like you're looping. You're gonna be looping, right? So now, if we check the high level language, you'll see when it comes to C++, when you're comparing it to the assembly language, it will be simple for you to understand how, if when I want to loop, I'm using a while loop this side for me to be able to go back and forth. What will I be using on the assembly language? You say, right? Then now let's come to the business applications that are written for multiple platforms. Now, when it comes to the business applications that are written for multi platforms, which have different operating systems, we check that when it comes to a high level language, usually it's very portable, right? The source code can be compiled on each target operating system with minimal changes. So if let's say I created a code now, or I've compiled the code, then if I move it from one operating system to the next, let's say I'm upgrading from Windows 11 to Windows 12, right? And on Windows 12, this application is not compatible. But let's look at our phones, our devices. We remember that when we are moving from smaller devices to the upper devices, most of the devices no longer support WhatsApp, right? So it means that for WhatsApp to be supported on the bigger ones, it means that it has to be recompiled. That's why there are updates. That's why you have to update in most cases. But it's very portable because it's not that difficult to recompile a code because you just change few things then there. So it requires minimal changes. You say right. Then when we come here, this must be recorded separately for each platform, often using an assembler with a different syntax. What you say right. So and it's difficult to do what to maintain. Yeah, I mistakenly exited this slide. So and it's difficult to maintain. Now let's go back here. I think I have to go back and explain. So when you come back here, right, let's look at this. We have a x86 process. So let's say now the operating system for the other device is not 86 processor, right? So it means that let's say maybe it's 32 or any other value. It means that you must record this. You said right now. It means that the code that I've written here must be recorded for it to support on the other device, right? And we must use assembler to assemble that code. So here you see that must be recorded. It must be recorded. Yeah, I mistakenly pressed this thing, right? So it must be recorded with a different syntax, and it will be difficult to maintain because if you move to another application again, or another software, it must be recorded again. Move to a different operating system, must be recorded again. So, which also makes it easier to say that when it comes to both multi platforms and also single platforms, the high level language is the best one to choose, right? So now we come to the embedded systems and computer games requiring direct hardware access. Now these ones, it's easier to say that, listen, what they say, they require what? Direct hardware access. And it's easier to say that the one that is closer to the hardware, it's the system, is the assembly language. So it will be easier. So here, that's why we come and say, it is ideal because the executable code is small and runs quickly. The reason why it runs quickly is because it is closer to the computer hardware, right? Or the computer system or the computer language. So now, when it comes to the high level language, we see that this one produces too much executable code and may not run efficiently. The runtime may be too much, right? It may need to process, because there's a lot of compiling that must occur. It must go. You remember how does a compiler works, right? It first goes through uh, character by character, taking all those tokens, right? And then it creates those sequences, and then it tries to check the errors and all those. So this one will be having too much executable code, and then it may not run efficiently. So the runtime may be too much. So the best program is the one that runs quickly. So in this case, when it comes to embedded systems and computer games, it will be wise to use the assembly language. Now we come to the hardware device driver. Now, when it comes to the hardware device driver, now when we check, this one says hardware, you said right? It means that when we check assembly language, this one for the hardware access is straightforward and simple. Easy to maintain when programs are short and well documented. Reason being, I've stated that the assembly language is closer to the hardware. You said right. But when it comes to the high level language, it may not provide for direct hardware access. Even though if it does, right, it will require some awkward technique coding techniques. And for you to use these awkward coding techniques, you must be a pro code, right? You must be in the industry with a lot of experience. So it means that, and also this one must often be used, right? The awkward coding techniques, which will result in maintenance difficulties. Because not every coder will come with the same mindset. Remember, once you become a pro coder, in other words, it's not just coding that works, also how you think. So not everyone will be able to think like you. So if you created some awkward coding techniques, someone may come and not be able to develop the program further, all right? So now we realize that the hardware device driver and the embedded systems and computer games requiring direct hardware access are the ones which are more compatible with assembly language. And also, the business applications for both single platform and multi platforms are the most compatible with the high level languages. So it's simple to say that I can say now that you can rearrange this however you see how I do it myself. I put the business applications together, try to see what's more different about this too, so that when I am asked this question on how on to compare, usually you might not write the exact words which are here, but you must be able to explain that these words which are most common here are found in your explaining, right? In your explanation. So now let's go to the other slide, and uh, then we can just open this one. So when we come here on this slide, yeah. So I think we're just gonna come somewhere here. Yeah. When we come now, we have the virtual machines, right? The visual machine concept. So on the visual machine concept, we are told that each computer has the native language that runs on its hardware, right? and a human-friendly language, which is built above it. And these can run in two platforms. It can run in interpretation and it can run in translation. So also we should be able, so we will gonna see answer when we are going to answer some questions, right? Where you will be asked about translation and also the interpretation. So for now, for these ones, we're gonna be focusing on translation. But you should be able, first you must be able to interpret. So you must be able to interpret languages. Let's say I'm interpreting C++. I must be able to interpret this plus plus to assembly language instructions. Then the assembly language will be translated to the machine language. So we'll be looking at that. So when it comes to the translating languages, now let's look at translating languages. These are the most asked ones, right? Yeah, these ones are you're tested on them most of the times. So let's say you're given a statement. They say create a program that displays or that display the sum of A times B plus C. And according to C++, you're going to say C out A star B plus C. Then you close that. So given that you have this also right now. So when you come here, usually you are not only gonna write this, right? Obviously you have to initialize your A, B, C. So when it comes to initializing, when you initialize in assembly language, let's say here I had written int A, B, C. You see right now. So I initialize this. Now I say that when it comes to assembly language, when I'm initializing, first we're gonna use a register called EAX. So we'll talk about what type of a registers this. Or we have different types of registers. These are like data types, right? Like you see here, we had int, something like that. So we're gonna be looking at these registers. So any variable that we have must be moved into a register for you to initialize it. But you're gonna initialize one thing. So let's say initialize A. The other ones I'm just going to apply the either a multiply or add and all that, right? So first, what I do, I initialize A. I move A into a register EAX. And then the next thing says multiply B. Multiplying, you're allowed to say multiply without using another register, right? But for adding and subtracting and moving, you must write a register. You put the, the 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 operand. This is called an operand, right? You put the operand. So now this is an operator, operand, operand, operator, operand. So we learn what type of a language is the one that accepts two operands, which one accepts one operand. So we learn about those. Also, you can be asked in a quiz or test or multiple choice or exam. So you must know when do I use one operand, when do I use two operands. So first we move A into EAX, and then we multiply by B. So in other words, EAX contains EAX now is equals to. So here first EAX was equals to. And another thing here, we use this for comments, right? For single line comments, we use this. Then we learn about multi comments. This is used for single line comment here, right? It's not on assembly language, not used for closing. So now I say EAX now is equals to A. You said I'm just commenting here. When I move A into EAX, then now I multiply by B. Now I have this EAX will be equals to A times B. You say right now. So now I add EAX. I add C into EAX. Now it means that EAX will be EAX will be equals to A star B plus C. Let me try to wipe the screen. I don't know why is it doing this. So this will be plus B, yeah, plus C. So it's A times B plus C, right? And then we execute. We learn about executing. You can call write int if this contains integers, or you can do other things. We learn on how do we execute. So executing here is different. It's not like in C++ where it doesn't matter what you're executing. You just have to see out, right? So here, when you want to display, you're going to uh, call. You must call. Sometimes you call and so on. So we'll see with that. So we call write int, then we execute EAX. So for us to execute EAX, we must call write int in this case. So the output will be in a platform in a machine platform. We'll see this when we are executing, right? The output will be in machine platform. These are types of registers that we have there. And EAX is also somewhere here. So we'll also learn about this. So now we come to specific machine levels. We learn about level one, which is the digital logic, CPU, bus, memory, then the instruction set architect, right? Then we learn about the assembly language and also the high level language. So far, I believe we've learned about these two, right? One, two. Pascal, I know that the majority haven't learned about it, but those who are maybe learning them aside, for sure. So now here, when it comes to the high level language, the idea is how do you translate, right, to a high level language to a low level language. So usually our focus will be between these two. We say, right, our focus will be between that two. So now, when it comes to the high level language, let's go to the high level language. Let me say this. The high level language is okay. Let's go to the high level. So these are the data representations, right? So I think I might not have included it here. Yeah, it should be at the end because I want us to look at it at the end. So let's look at these ones, right? These ones fall under level one, the data representation topic. So usually I want us to first do this, then we can go to those. But then for me to first explain this, right? If we come to level two, now for the instruction set architecture, I'm sure the majority of is the first time seeing this, right? So this is the language that defines the computer's CPU. So this will be defining the CPU, which it will have to understand, and also it will be used to execute, right, those programs. So now, if we check here, this will be used for mostly the arithmetics, data manipulations, input or output. So this is the kind of interface that we'll be using. So also the registers, we're gonna be talking about them mostly when it comes to this part on what type of registers are they having fast memory locations. Usually, we'll look at such cases, right? And which ones are used to hold data. So also we look at the memory addressing nodes and how can we access such locations and how do we retrieve data? Because when you are busy writing these languages or these programs, we must know if I want to, let's say, store some data somewhere on a register, then I want to access it. How do I access it? All right. Then now when we come to the other one, I think it's the digital logic. When you come to the digital logic, CPU, these ones are said that we're gonna be using gate. So this one, the digital logic is for gate, right? So we're gonna be using a gate here to yeah to work around our explanation. So we know the AND gate, the OR gate, NOT, and so on. So those ones are the ones which we've done in CSC. So that's why I said that the one which you might be seeing for the first time is this and this, right? But this one you've done it and you've done this. So it will be simple for us to go through those. Because I'm sure There's no one who doesn't know what is 1 or 1. We all know that 1 or 1 is 1. 1 or 0 is 1. We all know that 1 or 0 or 1 is 1, right? So we're gonna be looking at such cases here, the gates. So sometimes we'll be asked to draw diagrams, and we'll have to use such cases. So that's why first we need to look at the data representations. So when we come to data representations, we realize that the topics that we're going to be doing, we're going to be looking at binary numbers. You know, those binary numbers, these ones, right? These are binary numbers. So also we're going to be looking at translating between binary and decimal, and also binary addition, integer storage. We will remember those second complement, right? So first complement, we're going to be looking at the integer storage sizes. These will help us to choose which storage are we using or which register are we using for this case. So when we talk about the registers, again now we looked at the first register, which is EAX, right? When we look at EAX, this EAX can be broken into two. We can break this into two. We can have AX, right? So the other one we'll talk about it, which is what? Then we can have uh, AL and A high. You see, right? So we can break this down further and further. So we'll talk about which size does this one contain, which size is this one, which size is this one. So far, let's say this is 32, this is 16, this is 8. All right. So this would be moving in that case. So we'll look at such cases to say this is the register which is compatible with this line of code, right? Then we'll look at that. The hexadecimal integers, we know those. And then we must be able to translate between the decimal to hexadecimal and also hexadecimal subtraction. Also, we're going to be looking at signed integers. We also have unsigned integers. So signed integers are negative integers. So we are saying that these integers have a sign. So if we look at a -1, these are signed. You say that it has a sign. In other words, I'm saying it has a sign. Then unsigned is just 1. This one doesn't have a sign. You say right. So it's called unsigned integer. So we'll be looking at those also to say the length of signed integers is this and this, and also the length of unsigned integers is this and this. Then we'll look at binary subtraction. Those binary subtraction are talking about those second complements. Then we'll look at the character storage, right? So when we come to the binary numbers, we have digits 1 and 0, which we know that 1 stands for true, 0 stands for false, right? And we have the most significant bit and the least significant bit. So we know that this is the most significant bit, this is the least significant bit. If I come here and add 1 here, it won't have so much impact, right? It's like if I come to your bank account and add 1 rand, it won't have a lot of impact. But if I come and add a number uh, before those zeros, it's gonna have a lot of impact. So let's assume that you have 1,000 rand, right? Then I decide to add 1 here. It's gonna have a lot of impact. But if you have 1,000 rand, then I come and add 1 here, it's not gonna have a lot of impact. You see, right? So those are the most significant and least significant. So when you come to bit values, now we remember this. How do we read these bit values, right? We know that 2 to the 0 is 1, 2 to the 8 is 258, 2 to the 15 is 2, 32768, and also 2 to the, I just took them randomly, right? So that we know this. 2 to the 2 is 4, 2 to the 1 is 2, 2 to the 3 is 8. So we're going to be using this to convert, right, from the binary to the decimal. So now we come to translating from binary to decimal. When it comes to translating from binary to decimal, we see that, let's say we're given a binary number, which is this, right? So the binary number is 4 zeros, 1010. So what I'm going to do here, right, is this. What you're going to do, how you do this translation, you take this one, you take 1 times, this is 2 to the 0. The first number, right, it should be 2 to the 0. This is plus 0 times 2 to the 1 plus 0 times 2 to the 2. Then this one is plus 1 times 2 to the 3. And this one's obviously going to be 0 times 2 to the 4 plus 0 times 2 to the 5, 0 times 2 to the 6, 0 times 2 to the 7. So when we check, the ones that are going to be having impact are the ones with 1, because the rest are going to be 0, 0, right? That's why here we have that the solution is 1 to the 1 times 2 to the 0 plus 1 times 2 to the 3, right? 1 times 0 to the plus 1, 2 to the 0 to the 3. So this gives us 9, because this is 1, this is 8. So translating from binary to decimal is simple. We can say that that one is a simple case. If you have to translate, you're just gonna use this direct method, right? It's so simple. Here, likely they won't tell you use this method, use this method. You just have to translate anyhow you feel like translating. As long as it's good for you, you're good to go. So now, when we are now taking the decimal back to the binary, remember when we were translating here from binary to decimal, right? The question is, why did we use 2? Why did we multiply by 2 to the exponent 8? We remember that the base for binary is 2, right? The base number for binary is 2. And also, uh, let me say this. Yeah, the base number for decimal is 10. So now we focus on this one of 2, right? We say that when I'm translating from binary to decimal, I'm going to multiply by 2. Also, when you're translating back from decimal to, now I want to move from 9 to binary, right? You can also use uh, you can also use the base. Remember, here I was multiplying, and what is the opposite of multiplying? Is division. So when we come here, we can come and only focus on division, quotient, and remainder when you're translating from uh, this from decimal to binary. And how do you take this? So the final solution will be taken going up. You see right there. So here's what we're gonna be doing. Let's say I want to translate 9 to decimal, right? No, I want to translate 9 to binary. So I'm gonna have 9 divided by 2, right? Then I ask myself, how many times does 2 go into 9? It goes 4 times, right? And leave what? And leave 1. So it's gonna go 4 times and leave 1. So this will be 4, 1. And then now what are we left with here? We're left with 4. You see, right? Then because it went 4 times, so you're gonna write the quotient here. The quotient must keep on coming down. So you write the quotient. So now we asked, if I divided this by 2, it's gonna go how many times? 2. So I must also write the 2 here, right? Then how many, or the remainder is 0. You say, right? Then this goes how many times? It goes 1 time. 1 leaves 1, nothing. You say, right now. So I must do this until I'm left with 0. So now I divide here. This goes how many times? 2 goes how many times into 1? It goes 0 time, right? Until I'm left with 0 on the quotient. That's when I can stop. Then we're left with what? So if we want to check what are you left with? If you take 2 divided by 1 divided by 2, right? You must just know that I'm always going to be left with 1. Or you can just, it's this, it's like it's 1 divided by 2. This gives us 0, 0.5. You can even do this without a calculator. Let me show you with this one. 9 over 2 gives us goes 4, comma 5, right? 9 divided by 2 goes 4, comma 5. What you do, you subtract this comma 5. You subtract this 4, right? You're left with the comma 5. The comma 5 is the same thing as 1 over 2. Then you multiply this by the base. The base was what? Was 2. Multiply this by 2. You get 1. So that our remainder was 1. So even here, 1 over 2 times 2 gives us 1. So the remainder is 1. So you see that here we got what? We got going up 1, 1, 0, 0, 1. If we come and check this, it's also 1, 0, 0, 1. Right? So it means that we can translate it back. So it's simple to translate this. Just have to look at. So this is how you're gonna write it, right? So you're gonna write division, quotient, remainder, just like that. So when they ask you, then you write the results. Then it's 3 marks here, right? So something like that. So now we come to the addition, the binary addition. So not to make the recording long, right? So we're gonna be ending here on the addition, on the representation, right? Then when we come back, we're gonna be looking at the integer storages, or maybe we can look at the integer storages. Then yeah, we'll see from there. So when we come to the binary addition, what we have here is that I'm gonna add these, right? I'm gonna put this together. Just that again, I was coding this, right? So it's difficult to put these digits and the plus there. So I just let me just put them like this. But I'm adding these digits. 0 plus 1 is 1. 0 plus 1 is 1. And 1 plus 1 is 0, carry 1. Remember, 1 plus 1 is gonna give us 1, 0. It's 10, right? And then we're gonna keep 0, we carry the 1. Then the 1 will be somewhere here, right? We say 0 plus 0, it's 0, plus that 1 is 1. Then the rest will become 0. So this is 11. We know that 4 plus 7, it's 11. We say, right? So now we can also edit this. So this is just for practice, right? You can go and edit this. I'm not gonna edit for you, even though it's simple. You can go and edit this and then you send to me. I want it in this practical form. So now we look at the integer storages sizes, right? We have the byte, we have the weight, the double weight, and the quad weight. So we also have the fifth one, which we'll talk about, right? It's not called any of this. So now, when it comes to the byte weight, byte consists of 8 bits. We know this one. This one for byte, I'm sure we know it that a byte consists of 8 bits, and the weight must consist of 2 bytes. That's right. And a double weight must consist of 4 bytes, and a quad weight must consist of 8 bytes, right? So this is what we must know. So now when you come to, so it's like you just multiply them by 2, right? 2, 2, 2, 2 when you're moving forward, right? Then when it comes to the unsigned ranges for the bytes, the ranges for the unsigned, they move from 0 to 255 for the byte. So if I check this, if I take this, let's say this must be written like this. If I take 2 to the bit is 8, right? Minus 1, I'm going to get 255. Then if I take this one, 2 to the 16, so you don't have to grab this way, right? You're only going to know this. This is going to be, if I check 2 to the 16, minus 1 is going to give me 65535. As long as you know the size, right, of this weight. Then we come to the double weight. Double weight is going to be 232 minus 1, which is about, the reason why we're subtracting 1 again, we started from 0, you see right there. So 32, yeah, we put 32, it's going to be this number, it can't fit there. And if we come to the unsigned quad weight, already you know the unsigned quad weight, it's going to be 2 to the this minus 1, you see right there. Then you get that weight. So it's simple as that. So If you check in the original slides, it's there, you'll see it. So you can use both. This one I just made it to be readable, right? And it contains important information that I know it's gonna come in a test. So in a test, they can ask you the largest unsigned integer in 20-bit. Already I've shown you that it's gonna be -1. You see right now. So let's check what's that. It's gonna be 10, 4, 8, 5, 7, 5. You see right. So I've already shown you that. So when we come to the hexadecimal integers, so if you are able to translate, so to translate this one, let's say translate from binary. So here it's like I'm showing you three things. Translate from binary to hexadecimal, right? So translating from binary to hexadecimal. It's simple for you to move from binary to decimal first. So it's like we're creating a bridge entity in between. We're creating a bridge entity which will be the decimal. So remember, even if I'm given this, I'm given this, and I want to translate to hexadecimal. I'm gonna divide this into 4. You see, right? And I check this. We know that for hexadecimal, from 10, 10 from 10, these hexadecimals move from 0 up until 9, right? Then from 10, they start having some meaning. From 10, this is A, 11, this is B, 12, this is C, 13, this is D. This happens up until F, right? 14, this is the E, 15, this is F, then 16, it's 16, moves, and so on. So now when we check this is what? Or maybe let's look at this. This is 15, right? This is 15. So when we check this, since this is 15, where we say that this is 15, and 15 in hexadecimal is F. You write F. This is 10. Remember, this is 10. 1010, right? And how do you know that this is 10? This is 2 to the 0, 2 to the 1. It's 2, right? 2 to the 2, it's 4. 2 to the 3 is 8. So this is 8 plus 2 is 10. Then you get 10. 10 in hexadecimal is 8. I've written it there. You see right now. So when you come to uh, 1, 1 is still 1. 1 to 9 is that the same, right? And 16, it's still 16. So 0 is also still 0, right? So now it means that when you come to this one, we check this. This is 8 plus 2 plus 1. So this is 10, 11. So this is going to be 11. Look, it's going to be B because 11 is B right here. Then we check this one. This is going to be 8 plus 4. It's 12. And what is 12? 12 is C. And this is going to be 3. So it remains 3. You see right? So it means that here it will be 3 CB. But also translate that to hexadecimal. So we can see that translating to hexadecimal, translating to binary, translating to decimal is simple. So now let's check the next part on already we have discussed it on how do we translate uh, from binary to hexadecimal. So let's look at this one. We divide this into 4, 4, 4, 4, 4, 4, 4, 4. And when we look at this one, this is 1, right? We look at this one here. This is 4 plus 2 is 6. Look at this one, this is 10. 10 is A in hexadecimal. Look at this one is, uh, say this is 15. This is supposed to be F. I should have written F there. Yeah. So we see that that's the case, right? So, because that's 15, right? So 15 is F in hexadecimal. So now, since we know this, and we can be able to convert anything, all right? We can be able to convert from decimal to hexadecimal and so on. So it means that uh, we can do anything for now. So, is there any question that you guys might be having? If you have any question, you can ask. If not, we proceed. Yeah. Then now we look at converting from hexadecimal to decimal. So remember when we were converting from binary to decimal, right? We're multiplying here by two, because that was the base of binary. But now the base of hexadecimal is 16. We say, right, so we must multiply by 16. So if I have this hexadecimal 3, let's check what the exponent is. I'm going to multiply this, the exponent 0, exponent 1, exponent 2, exponent 3. It means that here the base is going to carry exponent 3, here base will carry exponent 2, exponent 1, exponent 0. So let's check. So 3 times 16 to the exponent 3 plus the b, we know that it's 11 in decimal, right? 11 times 16 to the exponent 2. A, we know it's 10. 10 times 16 to the 1. And we know that 4, it's 4 there. So that means the same, 16 to the 0. And this would be the binary for that number. We say right now. So it would be simple converting from hexadecimal to decimal. So now, now if we check, so you can just confirm this, plug this in a calculator to check if I did write the correct number here, right? So I wrote 15,284, right? Let me check. Let me just plug 15 to the 0. Yeah, this is 15 to, oh yeah, yeah, I was supposed to have written 268. That's 268. I just plugged that in a calculator and I plugged the wrong number, right? So that will be 15268. So you just plug this whole thing in a calculator, it'll give you that number, right? So I think maybe I might have added something by mistake when I was doing that. Now, when it comes to converting uh, decimal to hexadecimal, now we're not converting. Remember that time on converting decimal to binary, we're dividing by 2 because 2 was the base, right? For binary, not the base of hexadecimal is 16, so we divide by 16. We do the same thing, right? And then I'm gonna check it like this. You see, right? So when I check this 422, when I check 422 divided by 16, I get 211 over 8, right? Which this is 26, comma 375. So I realize that the quotient here is 26. So I'm gonna write 26 there and write 26 here. Then I take this. This is 0, comma 3. I want to check the remainder here, you see right now. So I don't want you to start again when you're supposed to check the remainder. So I check 0, comma 375. I'll multiply this by 16. You see right now. When I multiply this by 16, I get 6. So that's the remainder. You see right. Then I come here, 26 divided by 16. Let me check 26 divided by 16. Here I get 13. If you have a calculator there, you can also check right on your side. 13 over 8. And 13 over 8 is 1, comma 625. And this, the quotient is 1. And I'll take 0, comma 625. Don't forget, you must also write the quotient here. 0, comma 625 times 16. Let's see what we get. Times 16. I get 10. So that is A. So I wrote 10, then I wrote A so that you can know. So yourself, you're only going to write A, right? So that you can know that why did I write A there. So I just wanted you to see that. So this is A, you say right, which is 10. And then now I'm left with 1 and divide by 16. Check 1 divided by 16. Here I get 1 divided by 16 and get 1 over 6, 1 over 16. And 1 over 16 is 0, comma 0.625. Instead of the remainder is zero. The quotient is zero here. So we stop, right? It's zero. Then when I take 0, comma 0, this times 16, when I take this times 16, this will be times 16 will be 1. You see, right? Then I take this going up, it's 1a6. Every time you're converting decimal to something, you take it going up. You see, right? So you must know that. So usually here we don't look at the octa, right? To know that we also have the octa. We don't look at octa in this case. We don't look at octa. So yeah. So now we come to hexadecimal addition. So this, I think we're on page 23 of 37. Like, so not to give you a lot of information. So what we're gonna be doing next, right? We'll look at the hexadecimal addition. We'll look at the hexadecimal subtraction, and then we look at the signed bit for forming two complements. Then we'll look at all these, right? And also the gates. These are the gates. I believe that the gates are the simplest. So, or maybe let's look at the gates for now. Then we'll come back to those ones, right? Because those ones I want to explain them in detail, and I don't want this to be more than 1 hour. So we have like 4 minutes left. So, so I'm gonna skip to from slide 23 to slide 29, right? Then we come to the Boolean operations. Now, for these gates, we have the not and or operator precedence and the truth tables, right? So when it comes to the not, we remember not is for negation. So when we say not x, we symbolize it like that, and we say x and y, we symbolize like that. X or y, we symbolize like that. So this is based on the symbolic logic. They say that it's by George Boolean, right? So now the truth table for not, if x, we know this one, right? If x is false, and not x will be true, and so on. Just the opposite. And when it comes to and you remember we take it as multiplication. So f, we take it as 0. So 0 times 0 is 0. 0 times 1 is 0. Uh, 1 times 0 is 0. So that's why there we have f. And 1 times 1 will give us 1. So this and operator says that it should this it will only be true if both statements are true. Remember from SMT 012, right? Or SMTB triple Z. When it comes to OR gate, here we see that I just that I didn't draw the gates here right now, but we'll see them when it comes to applying them in detail. When it comes to the gates or gate, this one says that at least one statement must be true, and we take the OR as a plus. So when we say 0 plus 0, the first one, it's a false. When it comes to false, plus true, it's true. True plus false is true. True plus true is true. So let's check between. Remember with uh, SMTH or SMTB, right? You were always starting with a true here, but when you come to computer, we start with a false first. Is that right? We start with a false on this. So when it comes to the operator precedence, now we look at the expressions not x or y. So I'm sure we know how to read these right now. Then when it comes to this one, of brackets. We start by the brackets. That's why here the order says or, then not. We start by completing the inside and then we apply the negation. Then here we start by the inside the brackets. That's why the order says and then or. You say right. So this one is just knowing both mass. So we come to table of this. And then we realize that here we need x, y, and we need not x for us to complete this. So we have f, f, t, 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 f, f. And also for the y, we have F2, F2. So I believe that we still remember how to write these two tables, right? If you don't, you want me to remind you, you can tell me, I don't understand, I forgot how to write this. Then I'll explain on the next uh, video. So now here, when you're going to apply not X or Y, we see that we're going to be using this two, right? So we say true or false, it's true. True or true is true. False or false, it's false. False or true, it's true. Because at least one must be true for this to be true. Then you can construct a true table for this one, right? You can do that practice. Make sure that you do it. So now, in summary, the key points that we looked at here, we looked at the assembly language that reveals the software construction at levels, like or low level language. So we looked at moving register to EX, moving cursor to EX. We looked at multiplying. We looked at adding, right? So also we looked at one-to-one relationship with machine language. We said that this one is closer to the machine language. So when you create a code using it, it may be quicker to execute because it's closer to the machine language. Also, we looked at each layer, which is an abstraction for the hardware or software. That time we're looking at comparing, right? Then also we looked at the Boolean expressions, which are vital for hardware or software designs. So you're going to be using those for designs, right? Yeah, and then that's all. So let's close that.